second day webinar. Yeah, today they're going to give a lecture on computer graphics. Then computer graphics, based on that, they're going to explain, and then they're going to solve the problems based on that. Yeah, you please utilize what they're going to explain. After, once you complete that, if you have any question, free to ask the question. Over to Murli and Yuvika.
Thank you, ma'am. Sure. Ma'am, is the screen visible?
Yes, yes.
Good evening, everyone. Myself, Yuvika, and my teammate Murli will be explaining about the topic of computer graphics. Firstly, we'll start with the introduction of what is computer graphics. Uh, Displaying any kind of image with respect to some large size on a computer screen would be difficult, but this is simplified by using computer graphics. Various techniques and algorithms are used in computer graphics. The way how we define computer graphics is nothing but the use of computer to create and manipulate pictures on a display device so that it's visually appealing also. It comprises of many software techniques that we can use to create, store, modify, and even represent the pictures. And for example, if you take any manufacturing company, let's say it's producing some product A, and we have to seek or see its sales for the past 5 years and require the data. So this will take a lot of time, and even memory is also based in storing the information. So using computer graphics, this method will be easy to understand. It can be even understood, be properly understood by a common man. In this situation, graphics would be a better alternative rather than just collecting the data and putting it somewhere and then retrieving it and seeing all the uh, data. How is it? Instead, we can use a graphs, which will be a proper way to even measure how these sales have gone, whether it's increased. It can be useful even in calculating the profits and losses, whether new products should be introduced. In this way, graphics would be used in real time also. Since a picture can be easily understood in a single look, now we will come to visualization of a three-dimensional object. We'll see that as you can see in the image here, that there is a truncated pyramid with an hexagonal base. Here we'll introduce a three coordinate system, that is X, Y, and Z axis. We'll place it in such a way that it is at the center of the screen. As a viewer, we will be able to only see the two-dimensional picture of it rather than the whole complete image. The dotted part will not be visible to the observer from the front of the screen. This is how visualization of three-dimensional object occurs. At a whole, we'll be able to only see the XY coordinates. We'll plot them according to the screen, and then the image is visualized in two-dimensional space. Now we'll see how actually linear algebra plays an important role in computer graphics. In computer graphics, we'll be mainly using matrices that involve 2D or 3D graphics, and it relies on many matrix operations. For example, in any of the games that you take, the characters in the game or the gaming environment will include some or the other kind of computer graphics. The 3D models which we use have several uses in computer-aided design, that is CAD, for engineering purposes also. And advanced scanning techniques such as MRI, 3D models of organs can also be helping in diagnosing and assisting in the treatment of the patients. And secondly, the process in graphics called as animation is also one of the application of linear algebra. Relationship of the 3D object in a three-dimensional space over time is also in games. It can be used, and in games such as Mario, which many of you would have played, here we'll have some buttons for the control of the object. He'll be able to move right side or accelerating towards the right by using the right key, and for jumping he'll be using some other keys. This kind of games will use vector addition and subtraction to calculate the overall position of the object or even velocity of the object. This is how linear algebra plays an important role in computer graphics, and it is used in many different ways. The mathematical structure of the computer graphics takes advantages of many operations and theorems. which are used and assist in 2D, 3D models in animation and its rendering. Nextly, we'll see computer graphics also provides the facility of viewing an object from different angles, and this we call it as transformation. There are many types of transformation. Today we will be mainly discussing about three transformations: scaling, translation, and rotation. Firstly, we'll see what is scaling. Scaling is nothing but it is used to either alter or change the size of an object. As you can see in the picture image shown here, an object here is of some dimension. Let's say it's of dimension 3. Here we have scaled it to another option of by increasing its width to 2 times and its height by 3 times. This is called as scaling, and we will scale the object by using a factor called as scaling factor, and this decides how the object is to be increased or decreased in its dimension. And there are namely we have two scaling factors, one through the x direction and through y direction, that is x axis and y axis. If the and the value of the coordinates can be decided, and it can be either increased or decreased. If the scaling factors, that is sx and sy, if they are not same, the scaling of the object will occur, but it will lead to either distortion of the image or elongation of the image, right, as shown in the previous image. If it is equal, we will have a uniform scaling, that is a square will be a square if it's scaled with equal scaling factor. Otherwise it will be into some rectangle or some distorted shape. If they are not equal, it's called as differential scaling. If it's same, it's called as uniform scaling. Next, Murli will be continuing with the problems based on scaling.
Yeah, thank you, Viveka. So now we understood what is scaling. So scaling is actually modifying in the size of an object. Okay. So coming back to scaling, you can do scaling in two ways. So I'll explain both the ways of scaling so that you will understand how linear algebra will play important role in scaling. Okay, firstly we take up first problem. Here they only already given the object, that is in two-dimensional view. So as the object is given in two-dimensional view, the z coordinates of each point are not taken into consideration. So we have to scale this so that the first case is that it should be scaled by a factor of 3. That is, scaling factor is 3 in x direction. So if in any problem they have given that it should be scaled in x direction, it means that it is unscaled in y direction because they have not mentioned it. So in the second case, we have the sketch is scaled by a factor of 3 in y direction. So first I understand what is this figure. So in figure you are having so-called it is in this figure, no, you are having 5 points. Totally you are having the 5 points. So you are having the trapezoid as well as you are having the inner part. So the thing here is that, so first next slide please. Yeah. So we'll see first step. So first step it was given that we have to scale the x-axis by 3 unit. So that means your scaling factor is 3. So this method what I am explaining is a manual method of finding the scaling solution. So first thing is we are going to identify the points. Here actually I told that we were having only 5 points. But here I am including 6 points only because we have to plot the sketch after scaling. So how that I'll explain now in detail. So first thing is that points are listed A, B, C, D, E, F. You can remember the previous image which I have shown, that is given already in the question. So according to that, A, B, C, D and E is nothing but again the A point only. You can see here again A point only is repeated as E and F is nothing but the interior portion. So first exterior cycle is covered, then the interior cycle is taken into action. That's the reason why A and E are same here. So the thing is that I have just from the figure, first step is that I'll just take up the figure and from that figure I'm going to separate x coordinate and y coordinate. And I have listed here. So x coordinate, y coordinate. Now the task is that I need to scale the x coordinate by the factor of 3. That means y coordinate remains unchanged. So what I'm going to do, only x coordinate I'm going to multiply in terms of like into 3 into 3. So total column, that is second column, is multiplied by factor of 3 to get the fourth column. Now they are asking to plot the scaled view. To plot the scaled view, now x coordinates are already transformed by the action of scaling. So now we have to take the newly formed x coordinate with the y coordinate. That means you have to use fourth and third column to plot the view. Next, please. Yeah. So that's what I have plotted. Now you can just you already visualized that question figure, and now you can see this figure. So along x-axis it has been scaled by 3 units, making sure that y-axis remains unchanged. This is what this one. Next, please. Yeah. So second part of the question also says that now the y coordinate has to be scaled by a factor of 3, making sure that x coordinates remains unchanged. The same thing as I did before. The only thing is that now I keep x coordinates as same and y coordinates I am going to scale by a factor of 3. Now to plot the scaled view, I am going to take the second column and fourth column because y coordinates has already been transformed by the action of scaling. Next. Yeah. Now you can see that along x direction, the question problem and the question sketch and this sketch. So along x direction it remains same, and but along y direction it has been scaled. So this is what the view is. So I just tell summary what I did. So first, from the image, I have been taken each and every point coordinates, and that coordinates I separately tabulated, and whichever the thing I need to change or I need to scale, that one I have been scaled, and with the new scaled values, I'm going to plot the again. But the thing is that is it not a huge big process and time consuming and also there is no chance of getting error? Because if it is only 4 points, 5 points present, then it is okay. But if you're just visualizing a complicated object with around 13, 14 different points present in the two-dimensional view, then it would be a little difficult. So this is where the linear algebra comes into picture. So next, please. Next, please. So now the thing is, you got to know how actually the scaling is done with the previous problem. Now we'll see how that previous problem can be simplified. So that is possible only because of this aid of linear algebra. So you know that there may be to maximum extent many axes. Like if you are just visualizing the two-dimensional object, then you will have two coordinates, that is x and y coordinates, and it will have a number of values that depends on the point. And if you are taking three-dimensional object, then you will have three coordinates. It's simply like if you are just in the mobile, you are seeing some object that is three-dimensional object. It is keep on rotating. Now that object is nothing but three-dimensional. Now what you do, you just take a screenshot. After taking screenshot, if you see that screenshot, that will be no more a three-dimensional, right? It will be converted into two-dimensional because only your video screen is the plane there, and you will be having number of points. Okay, keeping that aspect in mind, so I will just in this aid of linear algebra process in scaling, I'll just consider that different points are exist. So I'll take P1 point. It is having again three coordinates because anyway for visualization purpose you have taken it as two-dimensional, and from three-dimensionality you are converted into 2D view. But you should have a monitor over z axis also. Suppose you are taking x and y. So in that respect, I am taking P1 x1 y1 z1, P2 x2 y2 z2, so on Pn x and y and z1. So now the problem was that if we did with the conventional method, the problem which I explained earlier, the problem was that we were having a lot many columns, rows, and you have to compute each and every one, you have to multiply. That's what becoming the hectic. So for that, now I'm going to introduce a coordinate matrix. So coordinate matrix means it is nothing but it's a matrix whose each column is nothing but the coordinates of the points. So next, please. Yeah. So in the previous case, I told the coordinate points are x1 y1 z1, x2 y2 z2, so on xn yn zn. So now I told even definition of coordinate matrix. It is nothing but the matrix in which each column. So if for example, you can take the coordinate matrix as P. Here in this coordinate matrix, first column is x1, y1, z1. That means this x1, y1, z1 is nothing but the coordinates of first point P1. Correct? No? So similarly, x2, y2, z2 and xn, yn, zn is the coordinates of the point Pn. So this is how I construct the coordinate matrix. Next, please. Yeah. Now we'll see. Okay. Constructing coordinate matrix is same for all scaling, translation, and as well as rotation. Now we'll see what is the scaling process actually is. So you can see some distinction in the image below. You have been listed as A and B. A is comparatively small, right, when compared to B. That means B has been increased its size. So scaling is simply nothing but modifying the size. It may be increasing in the size or maybe decreasing. So okay. So for that scaling process, you want a scaling factors. So for example, in x direction, the scaling is taking place by a factor of alpha. In y direction by beta, and in z direction by gamma. So we consider that. That means now if you have any point pi of xi, yi, zi, after scaling it gets converted into alpha of pi, alpha of xi, beta of yi, and gamma of zi. Clear, right? So the thing is, I'll just revise again. So you have a point xi, yi, zi, and we have already told that by alpha factor the x-axis is scaled, by beta factor the y-axis is scaled, and by gamma the z-axis is scaled. That means each point corresponding to x-axis will be multiplied by a factor of alpha, and each one corresponding to y-axis multiplied by a factor beta. So similarly with z-axis as gamma. That's why you are getting alpha of x1, xi, anything that may be, and beta of yi and gamma of zi. Next, please. Yeah. So now coming back to scaling process. So I told alpha, beta, gamma. So now you consider an object and you are going to scale by some factor alpha in x direction. Will it affect y and z direction? Definitely not. So because you are just scaling the x direction, making sure that I told in first problem, x direction is scaled, making sure that y and there it was only y direction remains unscaled. So for that reason, in order to build the scaling matrix, because we already know what is coordinate matrix. Now to build this scaling matrix, no. So for the first one I told, by x direction is scaled by a factor of alpha. So alpha 0 0 here because so x direction is scaled by alpha factor. That scaling of x direction is independent of y and z direction. So it is 0 0. Next 0 beta 0. That means if you are scaling y direction with a factor of beta, then your x and y is x and z is independent of that process. Similarly 0 0 gamma. Okay. So you consider any point, like for example pi of xi, yi, zi. Now once I need to scale. Scale means how? You are just going to multiply by some factor. Same thing here. If you are considering any point, you have to multiply that point with the scaling matrix so that you are going to get the what I can tell, transformed point or scaled point. So if it is a point, if you want a coordinate matrix, so total points will be covered in coordinate matrix. As we know that coordinate matrix is nothing but you are just making a column representation of each coordinates of every point. So similar, So that transformed coordinate matrix, we can call it as scaled coordinate matrix, because here transformation is nothing but scaling, right? So we can tell it as a scaled coordinate matrix. It is nothing but equal to the scaling matrix into, this is the matrix multiplication between scaling matrix as well as the coordinate matrix. Next, please. Yeah, so we'll just brief out before going to problems. So see, usually you are having 3D view, as I told. So now you are seeing a 3D object. Next, you have just taken a screenshot of this 3D object, so you are getting it in a view 2. Now what I did I just taken up some factor in which x and y direction is changing. Then you are getting the view. This is what we did till now. Next, please. Yeah. So this I already explained. I just recollect it firstly. So the coordinate matrix, I define it as a P. It is nothing but see, each column is nothing but the coordinates of a point x1 y1 z1 x2 y2 z2. Then transformed coordinate matrix means after the coordinate matrix after being undergone several operations, what the matrix you get, that is called transformed coordinate matrix. Your operation is nothing but scaling. So you're just going to scale or you're going to modify the size. So you're just going to multiply s into p so that you will get the p dash. Next, please. Now you will appreciate what is the effect or what is the impact after being introducing this coordinate matrix, say scaling matrix, transform coordinate matrix. Because same type of problem which I did as an example one, so same type I am going to, I have taken almost same type, and now I will do how easily this can be done in scaling. And this is even as an one of the important question, because this is from a textbook. Okay, so listen to it carefully. So in some questions, so they may give vertices. They have given a view of a rectangle with some vertices, and they also even given the view. But sometimes they only give the view, or sometimes they only give the vertices, but both being the same. Okay. So here is the rectangle, and each one with vertices, x, y, z coordinates of each points are given. Now my first task is to find the coordinate matrix. Second task is we have to find this coordinate matrix and scaling matrix after it is scaled by a factor of 2 in x direction and 4 in y direction. Then once after that is scaled, what will be my sketch of scaled view, that also I have to show. Next, please. So here the thing is simple. You already know how to find the coordinate matrix. So one part of your work is done. That means what you will do, you will just whatever the vertices are there, or whatever the coordinates are there. So initially it will be in the form of a points, the coordinates of each points. Now you convert it into matrix simply by making sure that you are writing that points, whatever the coordinates are there, in as a column, and that is enclosed in a matrix called coordinate matrix. So there you are having 1 comma 1 comma 0. I have written this as a first column. Next you are having 10 comma 1 comma 0, second column. So similarly I am going to frame the coordinate matrix. So first part of the question is done. So second part of the question they have given is that that view what you are looking. So in that view, x direction is scaled by 2 by the factor of 2 and y direction by the factor of 4. Again, scaling matrix I have already explained in definition. X direction is scaled by a factor of 2 means it is 2, 0, 0 as a first row of the scaling matrix. Correct? No? Because x direction is scaled by 2, but y and z is independent of that process. Next. Again, y direction is scaled by 4, x and z are independent, so it is 4. Have they given anything about z direction? No. That means z direction is unscaled. But you should not use 0 here, because 0 makes something like identity of z direction only not valid. So z direction remains unscaled means it is as before. That means you need to use 1 in the z. Then in x and y you can take 0, 0 because again if it is unscaled also both the process remains unchanged. So you have found the scaling matrix. The thing is that you have coordinate matrix and you have a factor in terms of matrix, that is scaling matrix. You just multiply, you will get the transformed or scaled coordinate matrix. So I have obtained the scaled coordinate matrix as below. Next please. Yes. So whatever P dash you are looking, it is the scaled coordinate matrix. Now my task is vice versa of what I did in the beginning. In the beginning, I was having points. I was having points the like with in terms of coordinate, x coordinate, y coordinate, z coordinate, like 110 something something like that. I was having. I converted into matrix. Now I need to again plot, na. So I have to convert from the matrix format into again coordinate points. So what I will do? So I know that in the transformed coordinate matrix or scaled coordinate matrix P dash, each column represents the coordinates of points of transformed view. So I'll just take them in that manner. So 240 is my first point, 24, comma 0 is second point, so on so I will take. Now with some suitable scale, I am going to sketch and plot it. This is how simple it is. See, how much of the work has been reduced. Instead of maintaining the number of tables, instead of individually multiplying x with something, y with something, then take that transformed one carefully and you are going to obtain. That you can't do directly with 5 points. If 5 points are there, first you have to do whatever external plotting, then internal. So all that task has get reduced using this concept of linear algebra. This is what I wanted to convey. This is about scaling. I'll just revise for just 1 minute so that you will get to know about everything. The thing is that first you will get in terms of either they'll give a view. From that view, you have to collect the points or directly they'll give points. The thing is, using that points, you have to frame the coordinate matrix. Once coordinate matrix is framed, then you have to make sure that in x and y direction or even in z direction, with what factor it is scaled. And you are going to frame the scaling matrix. Once the scaling matrix and coordinate matrix is done, you are just multiplying that matrix multiplication between scaling matrix and coordinate matrix to get the scaled coordinate matrix. Once again you got scaled coordinate matrix, obviously you get in the matrix form. So you have to just take up that matrix form into the, again in the form of a points with x, y and z coordinates, and you are going to plot it. So simple it is. Next please. I hope scaling is clear. Scaling is simply you are modifying the size using a scaling factors. Only 3 things that you have to remember major is that what is coordinate matrix, what is scaling matrix, and what is scaled coordinate matrix. Here you are going to multiply scaling matrix multiplication between scaling factor and the coordinate matrix. Okay. With this clarity, we will go to translation. So as I told, scaling means you are going to what you will do. You'll just increase or reduce the size. But in translation, you don't do that. You are going to just displace, dislocation of the object. So now the object is at one place. I am going to dislocate to other place. That means each point's x, y, z coordinate will get changed. That's what is called as dislocation. So that is nothing but your translation. So you can tell moving of an object, displacing of an object, dislocation of an object. So these are nothing but translation. I think you got clear idea what is translation. So just you are going to move an object. It is at some particular location. You take in with respect to xy plane, it is having some specific location. Now I am going to displace from that location. I am going to move into new location. So you can take these examples. So in the second example, it is simply it is been explained. So the point was O, then it has been dislocated to O dash. That means for x old, you are adding some factor, some translating factor tx, so that you are getting the x new. Similarly, for y old, you are going to add the translating factor in y direction, so that you get y new. See, here I am preferring to tell adding, correct? No? So I am telling x old is added by some factor, because it was in some position, you are going to add some other position or to subtract, whatever it is. Addition means that you are going to change the position. So there you are doing multiplication, correct? Na? So scaling factor, you are multiplying to the coordinate matrix, but here it's not. You are going to add the translating factor. So next, please. Yes, now we'll see how the translation will take place. Okay. So there what we did was for a scaling matrix, to frame a scaling matrix with respect to each process, we did separately. Like first, you are going to scale the x-axis considering y and z is independent. That's how I got first row, second row, third row of scaling matrix. Now I'll explain how to frame the translation matrix. So firstly, in the problem, usually they give translating vector. That means with that vector, with respect to that vector, your object is been translated. So what you have to do now? For example, you have x1, y1, z1 as one point. Now you have been given. It is being translated by x naught unit in x direction, y naught unit in y direction, and z naught unit in z direction. So that means that you are going to add that x naught unit to x1, correct? Na? Similarly, y naught unit to y1, z naught unit to z1. Okay. So, for example, for first point, if you have to add x naught, y naught, z naught individual unit, then what will be my first column of translating with matrix? Is it not x naught, y naught, z naught in a column manner? Yes. Okay. So second point, see the total object is going to be translated, then each and every point also will get translated, correct? So if one column, or you can tell one point is translated by x naught, y naught, z naught, then each one should be by x naught, y naught, z naught. So that you will be getting x naught, y naught, z naught, x naught, y naught, z naught as a column till the order of the coordinate matrix. That means you have to keep in mind here the order of translating matrix as well as the order of coordinate matrix must be the same. So next, I already explained in translation you're going to add something. That is, for example, you can tell an object is at 0 distance. Now you are going to push it by 5 meters. So it has been taken up the new distance. That means you are adding that 5 meters for it to move. That is what here translation is taking place. So whatever here translated coordinate matrix will be there, it is nothing but sum of, not product, here sum. So sum of the coordinate matrix and the translated matrix. Next, please. Yeah, you will get clarity if you go with one example. So this is also an example from textbook. So please do listen it carefully. Okay. So again, same. So sometimes they give only view. So be careful how to take from view. So if so is the case, then in that below image you are seeing, in that only they will write the points like 0, 0, 2, 0 like that. So here anyway that is not mentioned, but they have been given in the thing. So here given a square with vertices 0, 0, 0, 2, 0, 0, 2, 2, 0, 0, 2, 0. Here the thing is you have to write the coordinate matrix. Hope by the time I am reading the question, you would have already written the coordinate matrix in your book. Is it not? Because it is same as before. Only thing is each point you are writing in the form of a column. Correct? So it is nothing but the coordinate matrix will have first column 0, 0, 0, second column 2, 0, 0, third column 2, 2, 0, fourth column 0, 2, 0. That's all. Your coordinate matrix is done. So next question is that find the coordinate matrix after it is translated by a vector -1, 1, -2 transpose. That means here they have given translating vector. Here also you are done with translating matrix, I guess, because I have already explained. If -1, 1 and -2 is the one that is translated for first point, that would be same for second, third and fourth point. Yes. So you are writing this translating vector in 4 columns. That's all. Your work is done. Now you are going to add it with coordinate matrix and you draw the scaled view. Oh, okay, sorry, translated view. Okay, I will just explain that in the next slides. Yeah. So as you know, I already told how to frame the coordinate matrix. Okay. Translation vector is given. Yes. So I told previously, you should have the order of coordinate matrix and translated matrix to be equal. See, it is a basic general knowledge because matrix addition is possible only when both the orders are same. That's what here also, because we are adding two matrices. That's why. Okay. So whatever translated vector is given. So for first point corresponding to point 0, 0, 0, it should be translated by -1, 1, -2. So I have written first column. With respect to second column of coordinate matrix 2, 0, 0, I am going to write -1, 1, -2. So in that manner, I am going to frame the translated matrix. As I told already, operation P dash is equal to P plus T. So we are going to add it to get the translated coordinate matrix P dash. Next, please. Yes, you have got P dash. See, so simple the question is. It's almost same as scaling. The only thing is here, there we were using scaling matrix. Here you are using translating matrix. And there you are getting the scaled coordinate matrix. Here we will going to get the translated coordinate matrix. There you are multiplying the scaling factor. Here you are going to add the translating factor. So that's what the thing. See, I want to just convince you with that image. See, in previous image, the view they have given in question, it was in first coordinate. But here it is not. It has crossed the first coordinate. You can see that naming 0, 0.5, 1, 1.5. This is the power of translation. So it has been translated to some of the negative values also, because there it was both x and y were positive. But here it's not the case. So x direction with respect to that, y direction also is having some negative value. That's what this translation is. So you should have to remember that in translation, usually you are going to move the object. When you are moving the object, each point of that object will be moved. By what factor? By a translating factor. And that translating factor will be same for all points. So that's what the thing is. So here also process remains same. First you will be given with the figure. You have to identify the coordinate points, and that point you are writing in a column manner, getting the coordinate matrix. And from the translating vector they are given in the question, you are framing the translating matrix, add them both. Now again you get the matrix format. So from that matrix format, you are going to obtain the coordinate points, and again you are going to plot it. So that's all. It is simpler. So next, Yuvika will continue with rotation.
Um, yes, rotation is another transformational operation. Here we'll actually change the angle of the object in which it is there. Like I'll show you in this image, if this is the original point of the object O, it should be rotated with respect to some angle and with respect to some point. Here we take theta as the angle to be rotated, and origin will be the point of rotation from the original point to the rotated point. And rotation can either be clockwise or anti-clockwise. In this case, it's anti-clockwise, and the point of rotation is also called as a pivot point or rotation point. Here we have the initial coordinates to be O. We take the points to be x old and y old, and initial angle will be phi, and the rotated angle will be theta, and the new coordinates will be x dash and y dash, or x nu and y nu. For in order to rotate an object, we have to rotate with respect to some point. So here we take a point P to be x and y, and it should be rotated with an angle A, and it's originally at an angle of B from the x axis, and the calculation of the x and y axis will be as follows. We take the point x in terms of cos and sine. So it will be in terms of x will be r cos theta, cos B, and y will be r sin B. X dash will be r times of cos of a plus b. Here a plus will be, b will be the complete angle from the x axis till the point which is to be deflated. That is, the rotation angle is taken as well as the original angle is taken. We know the formula for cos of a plus b. We are applying it, we'll multiply it at the end we'll have the new coordinate to be x cos a minus y sin a. Here r cos b we have taken as x, that is replaced, and we'll have the new coordinates to be this. Similarly for y dash, r into sine of a plus b, the same a plus b will be the complete angle, and sine of a plus b is expanded. Then we'll replace r cos b to with x and y respectively. Our coordinate y dash will be sine of x sine of a plus y sine of cos of a. In terms of matrix form, we will be writing it as the rotation matrix will be written as written in this way with respect to cos and sine, and the old matrix will be multiplied. In this case, the x old and y old values will be taken. Theta will be the original angle. With respect to that, we'll be able to find the new coordinates of the rotated object. We'll go with the problems so that you'll have a proper idea of what rotation actually is. Here we'll have a given, the question is like, there is a line segment with the starting point as O and the ending point will be 4, 4. That is, it should be rotated to that with ending point as 4 in the sense the line coordinate starts from the origin and it ends to at 4, 4. We have to apply a 30-degree rotation in anti-clockwise. They have mentioned it as an anti-clockwise, and we have to find the new coordinates of the line segment after being rotated. So we have been given the data of x old and y old, that is 4, 4, and the rotation angle theta is taken as 30 degree. So we have to find the new coordinates of the rotated line segment. We have to apply the derived rotation equations for x dash, that is x new. We have x old into cos theta minus y old into sin theta. Theta as given, it's 30 degree. X old and y old, they have given the coordinates to be 4 and 4. So we'll substitute it, and at the end we'll have a value of 1.46 for the new x coordinate. Similarly for y coordinate, we'll apply the rotation equation, that is x old into sine theta plus y old into cos theta. We'll apply the theta to be 30 degree, and at the end we'll be having 5.46. So these are the new coordinates to which the old coordinates, that is 4, 4, will be rotated. And this is how it will actually look. First we have the line segment that is at some point 4, 4. After being rotated at an angle of 30 degree, we'll have a new line segment that is starting from the origin, but with the new coordinates, that is 1.46 and 5.46. This is how a line segment is rotated in anti-clockwise by applying rotation equations. Next we'll see with a triangle, that if it is rotated with if it is rotated by an angle. This is another example in which we have triangle coordinates, which is given as 0, 0, 1, 0, and 1, 1. We have to rotate the triangle by 90 degree. That we have to apply theta to be 90 degree in an anti-clockwise direction. We have to find the new coordinates. Since they have already given the old coordinates and theta is already given, the same we have to apply the same rotation equations with theta to be 90 degree. First, we have to take a single coordinate. We'll start with A. A is given as 0, 0. We'll be taking the old coordinates as 0, 0 to find the new coordinates with respect to this coordinate A. We'll apply theta to be 90 degree, and we'll have the new coordinates of with respect to A as 0, 0. So even after rotating that particular vertex, it will be at the same point as 0, 0. And next coordinate will be for B. We'll have here we'll be taking 1 and 0 as the old coordinate to find out the new coordinate. To find the new coordinates, theta will be the same 90 degree. We'll be applying the rotation equations. We'll find the new new vertices to be 0, 1. Here we have seen that it's rotated by 90 degree in this case. And in next coordinate, we'll go to 1, 1. New coordinates are found to be -1 and 1. This is how the image will look after rotation. This is the original image with 0, 0, 0, 1 and 1, 0. Here we, after rotating the triangle by 90 degree, we'll have the vertex A at 0, 0, B to be at 0, 1 and C to be at -1, 1. This is how rotation works. And next we'll have model paper problems.
Yeah. So model paper, okay, now till now you have seen some of the problems from textbook. Now you will be curious how the problems would be the one in model paper. So with that aspect, I'll be taking up the model paper problem. This is a 20 marks problem. Yes, this is a 20 marks problem that is being asked in one of the model paper. Again, now I think with me you can also start doing, because it's so simple now, because you have learned all scaling, translation and rotation. Only those things will be there here. Okay, so they are given again. Here also square with vertices. Vertices also given. Also the image is also given. You can refer anything. What is the coordinate matrix of the view? Just here I need to read, because you can do, because coordinate matrix is nothing but what? You are writing that vertices or the coordinates of that point in terms of columns. That's all. You will be having 4 columns, 3 rows and everything, then finish. Next, the coordinate matrix of the view after it is scaled by a factor of 1.5 in x direction, zero point 0.5 in y direction, you are going to draw the resultant scaled view. It is 20 marks now, so they covered everything. So you have one more case. You have to find the coordinate matrix after it is translated by a vector transpose. Okay, some vector is given, its transpose will find. Find the coordinate matrix of view after it is rotated through an angle of -30 degree along about the z direction. So I'll tell one more time before starting up this problem. If you have missed any part of our presentation till now, this is an opportunity for you, because everything is covered in this problem. Next, please. Yes. So first one is simple and you can do, that is you are going to fill the coordinate matrix. So with each point is written in the column manner, we have prepared the coordinate matrix. And my second question suggests that we have to scale in x direction by a factor of 1.5 and in y direction by a factor of 0.5. Yes, that means my scaling matrix will be what? 1.5, 0, 0, 0, 0.50, and here they are not mentioned whether the z direction is scaled or not. So it is nothing but z direction remains unscaled. So it is 0, 0, 1. Okay, so scaling matrix is framed. Now what we have to do to find the scaled coordinate matrix? You have to multiply the scaling factor. Yes. So P dash is equal to S into P. S is the scaling matrix and P is the coordinate matrix. So you are multiplying. Next, please. Yes, you are multiplying, so you get the P dash. So the thing is that you take roughly some scale and you just plot it. You know already how to just convert from a matrix to the vertices. So it's just simple. First column is nothing but first point. Second column, second point coordinates. Third column, third point coordinates. Okay, you get the coordinates and you scale. Now coming to next. Next, please. Yeah, so that is done. So first part is done. So first part was finding the coordinate matrix. Second part was you are going to frame the scaling matrix and you are going to multiply and get the that is scaled coordinate matrix. Now the third problem of that suggests that we have been given with the translation vector. Now you already know how to frame the translation matrix. You first see what is the order of coordinate matrix. I told it is 4 cross. No, it is 3 cross 4. Correct? 3 rows and 4 columns. So the translation matrix must also be 3 cross 4. Yes, 3 will be obvious because you are having 3 coordinates, x, y and z coordinates. So you get 3. That means whatever you are getting, that translation vector -2, 1, 3 should be repeated 4 times as a columns of this translation matrix. So that's what I have been written here. So next thing is, okay, so you already know, if you heard the word translation, then what you should do with translation factor? Yes, you should add it. You should add it to the coordinate matrix to get the translated coordinate matrix. That's what I did here to get the P dash. Next, please. Yes. So okay, again I got the translated coordinate matrix. Again same story. So I'll just take each column as a points, and I am going to plot it with some scale. Next. Yeah. Now rotation. Yeah, you recently, just few minutes ago, you learned about rotation. Okay. See here, they have been given that about z-axis, the rotation is with minus 30 degree. Can you guess about z-axis? If the rotation is minus 30 degree, what will be my rotation matrix? How to frame my rotation matrix? Because always framing rotation matrix is very important, because framing scaling matrix and translation matrix was simpler, but here it is little tricky, but I'll just explain with spending 2 minutes here because it is more important. And next problem is next model paper problem is completely on rotation, so please do understand this carefully. Okay. So, what it is given? First, I'll read out that title. So, the rotation about z-axis with an angle of minus 30 degree. See, the magic of this rotation is that if you are rotating about z-axis, your z-coordinates remains unchanged. Only x and y will change. Okay. So, with that respect, whatever you are making rotation matrix, so now it is above z-axis, so you can confidently write 0, 0, 1 because it is unchanged in z direction if it is rotated above z-axis. Now the question will arise, what if it is rotated above x-axis? Obviously, it is 1, 0, 0. Okay, y direction 0, 1, 0. Now your third row of the rotation matrix is clear. Now you will be thinking, what is that cos of minus something something? I'll explain that now. Okay. So now the thing is rotation about z-axis with an angle of minus 30. So above z-axis I have written 0, 0, 1. Next, after z-axis in a process you get what? X, Y, Z, again X. Okay. So, I think you have learned the derivation, how you will get the addition, that is cos of alpha plus sine of alpha, x naught is equal to x1 into. So, the same thing here. The thing is that here framing rotation matrix is, so as your third row is clear, now you come to first row. After third row, come to first row. See, if you are rotating above z-axis, then your third row is fixed. Then first and second rows z, that is third column, will be 0, 0. You just make it 0, 0. So I think now you understand. So third row will be 0, 0, 1. I explained. Now for first and second row, the last column will be 0, 0. That is the column corresponding to z. Next, remaining is 4. Now in rotation matrix, you are having 4 elements to be filled. For that, it is simpler. So after that, it is x. So it will be cos theta minus sine theta. Next, after x, you get y. Na? So for that, it is sine theta cos theta. So you have already learned this derivation. So I'll be telling the trick how to do it in the exam in terms of simplicity. Okay. So in the next problem, you will even get with respect to y direction rotated about. So there I'll even detailedly explain. But for now, to solve the problem, you understand that. So z about z axis, so it is 0, 0, 1. So remaining, that is third column I write 0, 0. So only 4 elements will be pending. That is by cos theta minus sine theta cos theta. That's all. So here theta is nothing but minus 30 degree. So you just write minus 30 degree. Now you get the R. See, here also you are rotating, correct? Na? So some factors is required to rotate that object. It's not just you are going to move by some distance. If you are just moving, you are just adding. But here you are not doing that. You are rotating. Correct? Na? So to rotate, you are going to multiply the rotational factor to the coordinate matrix to get the rotated coordinate matrix. That's what I did here, and I got the rotated coordinate matrix. So as again you got the rotated coordinate matrix. Now it is simpler for you to get it into vertices and you are going to frame the sketch. Next, please. Yeah, it is as follows. Next. Yeah, I told you one problem is exclusively on rotation, that too for 20 marks. If you have understood this problem, model paper problem 2, it is almost sure that you have been done with all computer graphics. It is little more trickier. So please do understand. I'll spend at least 10 minutes on this because it is so important. Okay. So from the scratch, from the problem, you please understand each and every step. Okay. So first thing is here they have been given following is the view with a coordinate matrix P is to be rotated through an angle of theta about an axis. See, you're seeing some line. So in that line, it is been rotated by an angle of theta. Okay, and they are given some specified angles for that. So with respect to x-axis, it is given beta, and with respect to y-axis, it is given alpha. Okay, if P dash is the coordinate matrix of the rotated view, okay, so they are telling P dash is the coordinate matrix. It is nothing but rotational matrix times the coordinate matrix. Okay, but here the thing is not that you are having a single rotation matrix, as I explained previously. Here the thing is you are having number of rotation matrix, and your task is to find what are that rotational matrix holds. I think question is clear. So here you are given such that P dash is equal to R5, R4, R3, R2, R1, P. Now your task is to find R1, R2, R3, R4 and R5. Okay, I'll just recollect it once again before going to the solution. See, they are being given with a coordinate matrix P, and after it is rotated by some angle theta. Here you don't bother what is the theta is. Here the thing is you need to find what all that rotational matrices are. So you take some angle theta, let it be theta, about an axis through horizon, and it is some specific angles are given, that is alpha and beta, and you are finally getting the P dash. So P dash is the rotated coordinate matrix, and here rotational matrices are 5, and you have to find all that 5 rotational matrices. So you are given with one equation. I'll just brief it out. See, here the thing is that first what you have to do, you are having x-axis. See, with respect to x-axis, that line. So you can tell like it's something a mirror image of z-axis. So you are seeing some line on that they have been given theta, the rotation symbol. So that line I am talking about. See, that line is making an angle of beta with x direction. See, here the task is not so simple. That's why we have to expand the task. See, they have given one point and they are telling it is rotated about an axis, but they have not mentioned what axis. And we can't see it is in XY plane. You can't tell that is rotated about Z axis. It's not correct. I just told it's a mirror image. For you to recognize that line, I have told. But it's not that it is rotated about Z axis. Now, here the rotation is not specific. Correct? Na? So, only for that reason, you have that R5, R4, R3, R2, R1. If not, they are not coming into picture only. Okay, I think now you are in some confusion. Okay, I will just clear it still more. Okay, see with that line is making an angle of beta with x. I think you agree. Yes. So now the thing is I need to rotate by an angle beta so that I have to rotate by an angle beta so that it should make cope up with x-axis. Okay, I have got coped up with x-axis. See, to get that angle beta, about what direction I need to rotate? See, about x, with respect to x direction, I need to make some angle, then I should definitely rotate about y-axis. So first one is clear. So you have to make sure rotation should be done by an angle beta about y-axis. Next. See, in the same image, you are going to see that with respect to y-axis, it is of angle alpha. That means I have to rotate by an angle of alpha, correct? See, once if you want to make an angle of y-axis to rotate by some degree, then definitely you should rotate about z direction. That is about z axis. Is it clear? See, now along x direction, I made that line to comfortably cope up with the x-axis, and next I made it to comfortably cope up with y-axis. Now it is clear now. What we should do? We should have to rotate about y-axis. Simple. Because previously we were not knowing about what axis we need to rotate. But here now we got an idea. Because I made sure that about x-axis it has come in line with the actual x-axis. Next, about y-axis, I made sure that it comes and coincides with the y-axis. Now the line is nothing but y-axis. So you are going to rotate about y-axis because rotation is on that line, and now that line is y-axis means rotation is about y-axis. Simple. Okay, I will make that rotation. Next, once I made that rotation of theta, see, it is wrong, right? Because I have changed everything. So that line I have changed. The direction of line only I have changed. That is wrong. So now my task is to get back it to original position. So I'm going to again rotate by minus alpha because in opposite direction than before. Correct, na? Before if I rotated about alpha, now I need to rotate about minus alpha to get back into original position with respect to y-axis. That is, I'm rotating about z-axis. Okay. Next, lastly, okay, you are having beta and you are having x na. So you have to get back to that beta position, what it is in problem to actual position. You have to get back. So for that, I need to rotate about y-axis. Yes, I'll rotate by an angle of minus beta about y-axis. I think problem is clear, but okay, I just explained the problem only. Even if you go with solution, will be still not clear. Next slide, please. Yeah, this is what I explained in the format of your understanding. So to solve this problem, you should follow these 5 steps. As it is 20 marks problem, you should give importance to each and every step in performing this task. Okay. So firstly, it is simple. You are not having a specificity on about what axis you are going to make the rotation. If that was clear, na, I would have directly framed rotation matrix and I just multiplied the coordinate matrix. I would have got the answer. That was a simple case which I explained in previous problem. So you understand, please understand the complexity of problem here. So first one, I already explained this, so you just read out. So first I'm rotating. Now the thing is, you visualize that question problem here while I'm explaining, so that if any doubt is present still, you will get to know. Okay, so first you are going to rotate by an angle of beta about y-axis. Yes, I told you, just recollect. Next, I'm going to rotate by an angle of alpha about z-axis. Next, I'm going to rotate by an angle of theta about y-axis. Then minus alpha about z-axis, and lastly, to come back to its original position, minus beta about y-axis. Now, okay, I have explained it clearly, but any point of time if you got doubt. See, it is not recommended, but still I tell some simple technique to remember. See, it is in the format of beta alpha theta minus alpha minus beta. And in the axis, it is yz, yz, y. See, this should not be followed. You should understand. But still, this is an alternative in final moment. Okay. So, first you are rotating by beta with respect to y, then by alpha with respect to z, then theta with respect to y, minus alpha with z, and minus beta with y. This is the steps. Next, please. Yeah. Now, the question is not this about what you are rotating and all. They are not bothered. They want to know what is R1, R2, R3, R4 and R5 actually is. So that is our actual task. We have to find what all that R1, R2, R3, R4, R5. Now I will just explain it in clarity. So this slide is most important and this is where you are evaluated for your marks. So just concentrate. So here, see, for first, here I have given for one, it means with respect to my first step. Okay, so with respect to my first step, what I am doing now, you just recollect yourself. I am rotating by an angle of beta about y-axis. Okay, so first step is nothing but you are rotating by beta about y-axis. Okay, now I have to frame the rotational matrix. See, problem if you know how to frame rotational matrix, the work is done because they are bothered about that rotation matrix. They don't want rotated coordinate matrix. They don't want. They want only rotation matrix that is responsible for rotation. Okay. See, I have explained in previous problem how to write the rotation matrix. Now just recollect it again. I will just explain. You see. See, okay. Here rotation is about what axis? It is about y-axis. Then what should be my second column? Because see, if I would have had whiteboard, I would have written. See, it is XYZ and here bottom also XYZ. It is in such manner it is indicated. Okay. So you just visualize. So first column in that rotation matrix is for that column the owner is X. For second column Y, third column Z. Similarly, first row X, second row Y, third row Z. Okay, this is how what I was up to explain you. Okay, now you have understood. Now I will just start to work out. See, what is the domain of y-axis? I told just now. It is second row and second column. Correct? Yes. So, if you have been asked in any question, the rotation is about y-axis, immediate work you have to do. Don't just bother about anything. You just write a matrix bracket and inside the second row and second column, it should make sure that it should be 0 and 0. That's all. Yes, it is done. See, in this first one, for 1, you are having second row 0 and 0 and second column also 0 and 0. Correct? That's what I explained. Next. Now, after doing that, how much will be left out? You will be left out with only 4 elements to fill the matrix. Now, you come to point. See, rotation about beta is secondary. Now, you are rotating about what axis? Y-axis. So now, if you want to rotate about y-axis, after y, what will be next element? That is z. That is next coordinate after y is z. So after that means now I told you one key and important point in the previous. I'll repeat again. See, if you are rotating about y-axis, your y coordinate will get will be unaffected. Only thing that will affect is the next one, their successors. That is z and x. So the coming successor is Z, right? So for Z, its position is 3p. That is third row, third column is only meant for Z. Correct? See, you write X, Y, Z along rows, X, Y, Z along column. Then you get third row, third column is exclusively for Z. So there you start your action. What I told, cos theta minus sin theta, cos theta. Now you frame it. That's all. So third row, third column, you write cos beta because your angle is beta. Then third row, first column, third row, first column is minus sin beta. Now come to first row, third column is sin beta and first row, first column is cos beta. That's all. So your matrix is framed. Next. Okay. Still confusion. I'll just take up with second one. Second case, as soon as you are seeing this second case, now you should have got the idea that here rotation is made by an angle of alpha about z-axis. See, that is very important. That 5 steps I have been written to make sure that you can easily get into this problem. So that 5 step or previous slide, you take a screenshot and please do remember that all 5 steps. Okay. So next, Okay, for this R2, yeah, R2 is rotation about what axis? About Z axis. If the rotation is about Z axis is owner of which row and which column. See, this is not technical term, but still you can understand the things easily. See, Z is mainly having its key feature in third row and third column. So you have to write 0, 0, 1 in third row as well as in third column. That's what I have got. Then I'll be left out with 4 elements. Now to fill that 4 elements, after Z, what is the successor that is going to affect? X. So for that X, it should be cos alpha minus sin alpha. Next, sin alpha, cos alpha. That's all what I have been framed. The important thing is you have to know where you have to use 0, 1, 0, 0, 1, that one, as well as where you have to put that cos minus sin, sin and cos. Then your work will be done. So similarly, again R3 is rotation about y-axis, and here the angle is theta. Next R4 is the rotation again about z-axis. But the thing here is that you are going in a reverse direction to get back into original position. So now by the end of R3, your rotation is done. But the thing is, you have to picturize it into its original position, because they don't want you to rotate. They don't want you to rotate randomly yourself and there you do your rotation action. They want it to be done in the position they mentioned in the question. So that's the reason why R4 and R5 I have written separately, because until R3 is my action to take up the rotation of theta, and after R3 this R4 and R5 are key responsible for just getting it back to its original position. So if I used alpha in step R2, here I need to use minus alpha to come back, that's all. So everything remains same as R2, only thing is wherever you have alpha you put minus alpha, that's all. Similar to R5 with respect to R1, wherever you have beta you use the minus beta. So I'll just revise the thing. See here, it is not that rotation about some specific axis is given. So what I am going to do, I am going to make it specific, because my rotation should be specific, because I should get some evidence about whether the rotation is taking place about what axis. So what I am going to do, I am going to just whatever the beta angle it is making, I'll just make it an angle of beta to come back to x direction. Then I just rotate by alpha angle to get back it to coincide with y-axis. Now I rotate by an angle of theta about y-axis. Again, I'll just come back to its original position by angle of alpha and beta respectively. This is the problem is. Next, please. Okay, to know, please take screenshots of these two quiz and try to solve by your own, because this is one level ahead of your VTU things. But the thing is, you will be get excited in solving these problems, and even we feel satisfied if you can get answer to these problems also. I'll just brief it out in just one minute for two quiz. Only I have given two quiz. Please just try to solve it and send us solution so that we'll tell whether it is right or wrong. So the thing is, here you have a coordinate matrix of order 3 cross 3. Coordinate matrix means the matrix you can find the determinant, because it is an square matrix. So they have given determinant as k, and they have scaled by some factor 1.6 along x direction and 0.7 along y direction. They have given bracket that z direction remains unscaled. If they are not given also, you have to take it as unscaled. Okay. So the thing is, you get the scale coordinate matrix. Now they are asking what is determinant of that. See, first of all, they don't want that determinant value, but they want what is its relation with previous. That's why they have given k, and the option is with respect to k only. Please do take screenshot and don't miss to solve. Next please. See, this is some more advanced than the previous. Here, by now I think you are very clear, because it's a part of your question also, that you have to find the scaled view or find the translated view, find the rotated view. Correct, na? So similar in that view aspect only, I have collected one quiz question. The thing is here also simple. they are given the coordinates points. So 0.200, like that you have given some points, and they have been given it is scaled by some factor along x direction, y direction, and z direction. Now they are not bothered about you to find the scaling matrix or to find the scalar coordinate matrix. That they don't want. They want what will be your shape of sketch. In two-dimensional view, if you are taking the vertices of T, that is called scaled coordinate matrix inverse. See, this is still more they are making you to think over, because they don't want you to find only shape of scaled coordinate matrix of that inverse. If that means, I'll tell one hint. If you get that whatever that scaled coordinate matrix, it will be anyway square matrix. If you find the inverse of that matrix and each column of that inverse matrix you take and you try to plot, you will get this thing. So you tell us whether it is a square or equilateral triangle, right angle triangle, or it's a straight line just passing through an origin. So please do take screenshot of this also and solve. Next, please. Okay, we are about to get to an end part of our presentation. See, I'll just brief it out simply in 2 minutes. What all you have learned, so that you can just get revised and you can even question us. See, you just understood what is computer graphics, and you have some three-dimensional object, how to visualize that three-dimensional object in two-dimensional view for simplified solving, you understood. Next, we explained about scaling, what is coordinate matrix, what is scaling matrix, and what is scaled coordinate matrix. Here, important thing is what we will do with scaling factor. We are going to multiply it with a coordinate matrix. Then you understood the normal scaling problem. Though that example one in our PPT is not important in terms of the exam, but it is somewhat important to for you to just appreciate the linear algebra. That's the reason why that first example is bought. From example 2 onwards, till everything is important. Okay. So after scaling is done, you've gone with a translation. So we explained what is translation, what is translating vector. Very important. That will be given in the question. From that, how to find the translating matrix, then to find the what translated coordinate matrix. Then you understood rotation, how to get the rotation factors, how to do the rotation, what is the rotation matrix, and how to frame the rotation matrix also explained for every axis. About any axis, how to frame the rotation matrix I explained. Next, we taken up some numericals. Yes, from many textbooks we referred whichever is important to you. Then we have taken the model paper problems. These two are important model paper problems. Then quiz and conclusion, what I am telling you. Next, please. Yeah, thank you. If you have any questions, you can ask now. Thank you.
Thank you, Muruni. Anybody have a question? Please free to ask the question. Muruni and Yuvika, they explain very nicely for rotation and scaling, both the factor, and also they taken 2 model paper questions. Apart from that, they taken some more, few more problems and they explain. Anybody have a doubt? Please unmute and free to ask the question. If it's not possible to ask the question, you please post your any question queries in the chat box.